Hello friends, our topic of discussion today is the threaded binary tree. I will just give an overview, a brief overview of what is a threaded binary tree in this video, and this is a very important topic for discussion on data structures. And threaded binary tree, you have already just studied the binary tree in detail in my previous video, and now I am going to describe this threaded binary tree in a nutshell. So I'm just going to give a brief overview of this threaded binary tree and what is the difference between the binary tree and the threaded binary tree. I'll just highlight on that. So threaded binary tree is nothing but a binary tree containing some sort of threads, left thread or right thread. Why thread? Because in the binary tree we have seen that some of the nodes can contain children and some of the nodes can contain no children or even can contain one child. So in that case, if any left pointer or right pointer or both the left and right pointers are null pointers in the binary tree, so those null pointers are not used at all. So in order to use the null pointers in an effective manner, so we implement the threaded binary tree in order to utilize the null pointers in a way so as to help us in the process of many processes like traversal techniques and many other processes. So this threaded binary tree, I'll just go on to draw a binary tree and add threads to that and explain what is a threaded binary tree and how it is drawn, how it is implemented, what is the structure definition of the threaded binary tree, and what is the use of the threaded binary tree. Everything will be discussed after drawing a pictorial representation of the threaded binary tree. So let me just draw a threaded binary tree in order to explain it to you. So suppose I am just drawing a binary tree like this. Suppose this is A. Suppose there are two children of A, B and C, and B has two children, that is D and suppose E. Now C has two children, F and G, and D has one child, that is H as the right child. H has two children on the left and right, that is J and K, and G has one child, left child, as I. So suppose this is a binary tree, and this binary tree, you can see that this has two children, this has two children, but this G has only one child. This F has no children. Since the F has no children, it can be called the leaf node of the binary tree. E is also a leaf node having no children. This J and K are leaf nodes, they have no children. I has no children, and D has only one child, that is the right child in H, and there is no left child of D. So there are many nodes in this binary tree which can be seen to point towards null pointers. Suppose these null pointers, if we just utilize the null pointers to point those null pointers to hold some addresses of other nodes, so in the form of threads, in that case we call this binary tree a threaded binary tree. So I will just convert this binary tree into a threaded binary tree by adding some threads to it. And how to do that, I am just showing you. Let me draw it and explain it to you. So suppose the rule is like this: if the left pointer to any node is a null pointer, then the left pointer of that node is going to have a thread which points to the Inorder predecessor of that respective node. And if the right pointer to any node is pointing towards null, then that null pointer is to be directed to the right Inorder predecessor I have taken in the case of left. In that right case, we are going to point it to the inorder successor. So, what is the inorder predecessor and inorder successor? Inorder predecessor is nothing but the node which comes in the traversal, inorder traversal sequence before that particular node, that is the inorder predecessor, and whatever and what node which and the node which follows the particular node, that is the node which is under consideration in the inorder traversal sequence, that is any node which follows, suppose any node, any particular node in the inorder traversal sequence, that node which follows the particular node is called the inorder successor, and the right null pointer goes to point to the inorder successor and the left null pointer goes to point to the inorder predecessor. Suppose if we just do the inorder traversal in this binary tree. So, let me just do the inorder traversal in order to write the traversal sequence so as to cross check what we are going to do here. Let me write the inorder traversal for the sake of understanding. So, suppose inorder traversal means left, root, right. You know this trick. Here left root right, we go to left root right, we go to left root right, left is not there, we come to root and print the root, that is D. Then we come to the right we say left root right at H, then we go to left, then we say left root right at J, there is no left, print the root J, then come to the right, there is no right to this J, backtrack to J, J has been printed, H will be printed now as the root, we go to the right of H, to the right subtree of H, to K, and we say left root right, there is no left, print the root K, there is no right, backtrack to K, K has been printed, backtrack to H, H has been printed, that is we have done with the left subtree of D. Now we have done with the right subtree of D rather, and D has already been printed. So, we are done with the now the left subtree of B. Now, we go to this B and print the root B, then come to this right subtree of B, E, then follow again the recursive approach, that is the left root right approach. There is no left to E, there is E, that is the root is at E. So, we print the root E, we go to the right, there is no right, backtrack E, E has been printed, go to B, B has been already printed, we are done with the entire left subtree of the root node A. Now, we are going to print the root A, and then after that go to the right subtree of A, left root right, left root right, there is no left, print the root F, go to right, there is no right, come back to F, F has been printed, left subtree of C has been done with, go to C, print the root C, then go to the right of right subtree of C, go to G, then say left root right, go to I, then again left root right, there is no left, there is root I, print the root I, there is no right, we get back to I by backtracking and see that I has been printed. We have done with the left subtree of G, then come to G and print the root G, and then go to the right of G, there is no right to G, get back to G, G has been printed, get back to C, C has been printed, get back to A has been printed. So, we are done with the entire inorder traversal. So, this is the inorder traversal sequence of the binary tree which has been drawn over here, and we are now going to add threads to the different null pointers in this binary tree by following the approach which has been discussed earlier, that is the left null pointer will go on to point to the inorder predecessor of a particular node, and the right null pointer is going to point to the inorder successor of a particular node. So, suppose this E, suppose we take this E has two null pointers because it is a leaf node, it has no children. So, E's left null pointer will be pointing towards the inorder predecessor of E. So, what is the inorder predecessor of E? See, the inorder predecessor of E is B. So, we will add a thread and point to B from the left null pointer which was there at E is now pointed to B to hold the address of B. So in this way the left null pointer of E has been utilized to hold a valid address of another node which is nothing but the in-order predecessor of this E. Similarly, the right null pointer will point to the in-order successor of E. And what is the in-order successor of E? In-order successor of E is A. So the right null pointer will be utilized by a thread to point to the in-order successor of E, that is A. So these are two threads added to the diagram. Now come to F. F has an in-order predecessor of A. So left null pointer of F will point to A. Right null pointer of F will point to the in-order successor C. I has two null pointers left and right. I has a in-order predecessor of C. So left null pointer go to point C. In-order successor is G, that is of I. The in-order successor is G. So the right null pointer will point to G. In the same way, let us see J. J has the in-order predecessor in D. So the left null pointer will go to point to D and the right null pointer will go to H, that is the in-order successor of J. K. K will left pointer of K will go to point H and the right pointer of K will go to point B in this way. So we have done with all the threads. No, we are not done with all the threads because D has one left null pointer and G has one right null pointer, and that pointer, since D has no in-order predecessor because it is the first in the traversal sequence, the left null pointer will be a thread, but this thread will be called a dangling thread. And similarly for G, since there is no in-order successor, the right null pointer of G will be again a dangling thread. So this is called a dangling thread, and this is also a dangling thread. Now I just move on to the declaration of the structure of this threaded binary tree. How to declare the structure of the threaded binary tree. So we'll write the structure in this way. Suppose any node of this threaded binary tree will obviously contain a data part, two pointers, one to the left child and one to the right child. So this will be there as in the normal node of any binary tree. In addition to those three fields, we will have two other fields, that is called the left flag and the right flag, which are integer variables. And I will just declare the structure and let you know what I have done with that. So first, let me write what is to be contained in the node of the threaded binary tree. So there will be a data part, there will be two address parts. This is the left child, this is the right child, pointed to the right child. This is the data part. It can be an integer data, cat data, float data, any type of data. And there will be other two fields, and this field is called the left flag and this field is called the right flag. So left flag and right flag are the two extra elements which we have added in the case of a node of a threaded binary tree. So let me write the structure like this. Suppose I am writing the structure: type def struct b thread node binary threaded binary tree. In order to just in order to make it clear that it is we are dealing with the node of a threaded binary tree, I've written the name B thread node. So B thread node means a node of the threaded binary tree, which is the structure of the topic of discussion. That is type def struct B thread node, that is a node of the threaded binary tree. It will contain, suppose, a data part. Here we have used character data, that's why I am writing char data, and now there will be two integer variables, that is the left flag and right flag. What it will contain, I am explaining it in a bit. Int left flag comma right flag, and then two pointers, that is struct B thread node star left star right, and name it as B thread node. So this is the structure definition of the threaded of a node of a threaded binary tree. So what is this left flag and right flag? Left flag is an integer variable which will contain the value 1 if a particular node has a left thread. So if a particular node has a left thread, then the left flag will be set to 1, otherwise it will be set to 0. If the right flag contains 1, if the right flag of any particular node contains 1, that means that there is a right thread as well. So if there is a right thread in a particular node, then the right flag variable of that particular node will be set to 1, otherwise it will be set to 0. So this is the concept which we maintain in the case of the structure definition of threaded binary tree. Suppose randomly we take this F node. Suppose F node will have a content like this. Suppose F node's data value is F. F node has a thread on the left side, that is the left flag of F will be set to 1 because there is a left thread, there is a right thread as well. See, this right thread points to C. So the right flag will also contain the value 1, and the left pointer will contain what? It will contain the address of the inorder predecessor of F. So here it will be the inorder predecessor of F's address. Suppose A has an address 655, so it will contain 655. And suppose inorder successor of F is C, and it has a address of 501. So this right pointer will have an address 501. So this is nothing but just an example to show how the value are stored in each node of the threaded binary tree. So in this threaded binary tree which we have drawn, we have taken an example of the node which contains F and written the contents of F node, the node which contains F as data. So this left pointer will contain the address of the inorder predecessor of F, that is 655, which is the address of A. The right pointer of the node containing the data F is 501, which points to the inorder successor of this node F, which is the address of C, that is 501. Since F has two threads, each on the left side and on the right side, then that's why the left flag will be set to 1 and the right flag will also be set to 1. So this is the approach which we have followed in this threaded binary tree. So if you have any doubts and queries pertaining to this entire explanation of this concept, you can well post your doubts and queries into the comment section below so that I can address them. Thanks for watching this video.